will immediately share my screen. And now you can see the lecture notes. So, last lecture we covered the energetics, which is quite an important topic. And now we rush onto the next topic, which is the moisture budget equation. And there will be some application to Sahel drought for this equation. Now, the moisture budget equation is a very important equation. And I don't think it will be covered in any of the other courses. So we want to discuss this here. It's a very useful equation that in many, if you apply, if you do analysis of rainfall, local rainfall adjustments, if you're interested in these kind of things, you will be doing this analysis in future, I'm sure. In many toolboxes that are used in climate, they have tools to calculate this essentially what we call vertically integrated moisture flux that turns out to become crucial. Okay, so in order to derive this equation, we go back to a first principle equation, essentially. So an equation for the mass fraction of water vapor in the atmosphere. There's an equation for this. And that equation, of course, interacts with the other equations in our thermohydrodynamic system. So far, we have essentially not made a lot of use of this equation. However, we have already seen that this equation interacts strongly with the thermodynamic equation, because if we have latent heat release, then this is due to a change in the water that, it's a change of the water vapor due to phase transition. So this is also what we call MV, is also called specific humidity, as you know, is sometimes abbreviated with Q in climate and metrology, but we call it MV in this case here. The definition is also that this is the density of the water vapor component divided by the total density of our air. So this is not the density of the dry air, but the total density of our system. And so the complete equation for this looks like we have a rho times the advection of this quantity, as usual. Then we have the convergence of fluxes, and these are now diffusive fluxes of this quantity, because the non-diffusive fluxes, they are included for the time being in this advection term. And we have a source term or sink term for this quantity, which we call S. This is a generic evolution equation that is valid for any tracer. Now, so this is the water vapor quantity. And we can imagine that this quantity is important, because we need to know, even in every climate model, where the water vapor is. Because then if we have locally lifting of air and we have moist air, that may immediately lead to condensation and rainfall and release of heat in those regions. Whereas if we are in dry regions, maybe not. The air may be so dry that we will never get to condensation. Now let's look at this distribution of this specific humidity. This is for near surface values of specific humidity. If we go up, this specific humidity becomes smaller. So at the surface, we have typical values of this quantity. Specific humidity is a dimensionless quantity in principle. Here it's the numbers are in kilograms per Kelvin. In order to make the numbers kind of nicer, otherwise you would have 0 point something, 0.0. But if you draw this quantity in kilograms per Kelvin, you get numbers that are in the order of 1 to 20 maybe, as we see here. Now this is for the annual mean. And so what can we observe? So what is the basic distribution here? Red is very high values, and blue and violet maybe are low values. So how is this distributed? This looks very much like the temperature distribution, no? It's also warm in the tropics, and that is where we have most of the specific humidity. And then it's cold in the exotropics, and there we have much less specific humidity. What do you think is the reason for this? Can someone make a guess? Why is this why do we expect this distribution in principle? Now, the main reason for this distribution is that this quantity, the water vapor in the atmosphere, can get to saturation. And if it's at saturation, you cannot increase it anymore, because the water vapor then will simply condense into water and rain out. So, and that depends strongly on temperature, as you have learned according to the Clausius-Clapeyron equation, as you have learned from your atmospheric physics course. So in regions where it's cold, the air can simply not hold so much water vapor. Any water vapor that is over some threshold has to condensate. And therefore the water vapor has to be smaller in colder regions. That, of course, doesn't explain completely this distribution. And there are also regions where for sure we have less relative humidity, for example, where the air is simply very dry compared to other regions. If, for example, if we go along in the tropical regions from east to west, we see, for example, in the deserts, obviously, it's dry, even though it's very warm. So this is not a one-to-one relationship. So it can be very dry there. The reason then is perhaps that there is not much water available for evaporation here, and therefore the air becomes very warm and the specific humidity stays still very low. But over the ocean in general, that's not the case. Where the ocean is warm, there's always enough water vapor available that that can evaporate. We will see that there's also not a one-to-one relationship between evaporation and this water vapor distribution, and in particularly also rainfall. We will discuss that distribution later. But in principle, we have these typical values that can go up to 20 gram per kilogram. So that's 0.02 that this quantity can get to. So it's usually a small quantity. Water vapor in the atmosphere can go up to 4%. So here we would go up to 2%, but it can go up to 4%. And it's highly variable. This is now just an annual mean distribution. But water vapor, if you were to look at the simulation of water vapor, that is carried around in our Rossby waves, in our cyclones, and condensates here and there. So that's an extremely variable quantity. So we have to know where it goes to. But our aim is to derive an equation essentially to understand regional precipitation amounts. We want to understand how can we explain a regional precipitation rainfall event in a generic manner. So the way forward is to derive from this equation here, which is written for the specific humidity, another equation which is written for this partial water vapor density. And you can, that is a very simple calculation that you can do as an exercise by using the full continuity equation. So you can show that then that equation looks like this. And now in this formulation, we may call it again like a flux formulation, then we do get not only a diffusive flux of this quantity, but also a macroscopic flux of this quantity in this new formulation. But otherwise, it's a one-to-one calculation. Now, this is more convenient because this we can now integrate vertically, because the dimension here is now kilogram per cubic meter of water. So if we integrate this vertically, we can get a quantity that is something like kilogram of water per unit surface of air. So that gives us the amount of water that can fall out of our column of air. Now we do this, we integrate this quantity vertically. We integrate simply this equation vertically. Here we can exchange then the derivative and the vertical integration. We integrate from 0, we assume we have a flat surface, to infinity. Now, that splitting for this divergence here, this is a 3-dimensional divergence. The vertical part can be directly integrated, and that gives us rho times vertical velocity at infinity minus at the surface. Now, if we have a flat surface, then the vertical velocity there has to be 0 because we cannot intersect the surface. And in infinity, the density of water vapor is 0. So the first term here drops out. But the terms that are remaining is the convergence of the horizontal fluxes, the vertical integral of the convergence of the horizontal fluxes. Further, we assume that the flux, this diffusive flux at infinity is 0. This is the reason, so that the density of water vapor goes to 0, but there's no flux if we go up. But at the surface, this lower boundary condition here, at the surface, this flux is not 0. But the definition of this flux at the surface is the evaporation. This is the definition of evaporation. That's our evaporation flux at the surface. So the amount of water vapor that goes from either water surface or land surface, or more complicated, leaves even at the land surface, into the air that is residing above. That can be complicated. To express this evaporation quantity in terms of, you have to parameterize this in the end. We can just write E, but in reality, in order to evaluate E, we would need a lot of information from the surface itself and from the atmosphere above, because you all know if you hang your laundry in a very dry and windy conditions, that will dry off very quickly. So there's a lot of evaporation when there's a lot of wind. But when that's not the case, maybe, and the air is almost saturated, then the evaporation is very much reduced. So it's clear that we can devise some rules how this evaporation should scale with wind speed, with the saturation deficit, and so on. And of course, with the moisture of the surface. But we simply say in this case, however we evaluate this, but this is the evaporation. On the other hand, the integral of the source term in this equation is simply the precipitation that eventually we can measure at the ground. That's the final precipitation. There can be also evaporation, but in the end, whatever we measure at the ground is already the net precipitation. So there can be more precipitation that is then evaporating, but what we measure on the ground is the net precipitation that is this final integral here. Then if we assume a stationary state conditions, of course there can be changes in the storage, that if you if you look at shorter time scale, those changes in the storage may be important. So there can be an accumulation of water vapor in the air, and then it's not immediately raining out, but the water vapor simply accumulates or decreases. But if we assume that there is a stationary state, then we get to the following conclusion. Oh, we also assume that then the diffusive flux here is small compared to the remaining horizontal diffusive flux is small compared to the macroscopic flux of this quantity. In that case, the precipitation that we have locally has to be equal to the evaporation and the convergence of moisture. This is for the stationary state, because you can imagine a situation where now we have a strong convergence of moisture. We assume here that if there's no evaporation, that immediately has to be balanced by precipitation. Of course, for some time, you could have some storage of that moisture in the atmosphere. But that we have assumed, because of the stationary state conditions, that this is not the case. So in a long-term, let's say, stationary state, probably even valid for monthly means, the stationary state condition, then this equation has to be valid. The precipitation can only come from local evaporation or a vertically integrated moisture flux convergence term, which is what we see here. Now this can be split, we can split this in a little bit further, which is also interesting. So we can split the moisture flux convergence into two terms. One is this is the specific humidity times the divergence, and the other is the kind of the advection of moisture term. It turns out that for most cases, if you evaluate this, for most cases, the first term is dominant. So if we are in a moist, the first term tells us if we are in a moist environment, any convergence, any horizontal convergence will lead to rainfall if there is no strong evaporation or other factors important. So any strong horizontal convergence will lead us to rainfall. Now, this is also consistent with the fact that we know that if we have horizontal convergence at the surface, the only way the air can go is to rise. And we know if the air is to rise, then the temperature will drop and the water vapor that is in the air has to condensate and the rainfall in the end has to fall out. So these two things come together. But there's another mechanism here. The second term here can be occasionally important, and this is kind of can be interesting to work out which of these terms are relevant. If you have a local, you find there is a local rainfall response, let's say to the El Nino phenomenon, but you want to understand, what is this due to? Is this just due to convergence of this convergence term, or is it due to advection of moisture air from other regions? So sometimes the second term, which is really you are perhaps in a dry region, but then there is an advection of moist air coming, and that can increase the rainfall. So sometimes it can be useful to try to distinguish these two terms, and we will see examples of this probably later. Now, the way this is often done is again using the pressure coordinate system, because all reanalysis and most of the model data that we are looking at still is usually posed in the pressure coordinate system on pressure levels. So we can simply transform this vertical integral that is here in z coordinates using our knowledge of the hydrostatic equation, if we use the pressure coordinate system, into this pressure integral. And then you can simply work out that again, we find precipitation is equal to evaporation, and then we get this alternative formula. And you will find this vertically integrated moisture flux convergence term. You will find this in many toolboxes that are used in climate studies. There will be, often you don't have to do it yourself. There will be toolboxes that do this vertical integration of the moisture flux for you. And then you can get the total quantity out of that toolbox. Because then with this quantity, you can assess, okay, is my local rainfall change due to a change in evaporation, or is it due to a change in the vertically integrated moisture flux convergence? Let's have again a look at some figures. Here are again the annual mean values of this is here, the top panel shows us evaporation, the evaporation field. And here we see again the yellow and reddish values are large, and then the violet and blue values are less. So the evaporation, as we can see, is maximized in the subtropical region. Why do you think this is the case? There's a lot of evaporation in these subtropical regions, and not so much where we have actually the warmest air close to the equator. There is evaporation, but it's not huge. So the reason is that we have in these subtropical regions, we have our high pressure systems, which induce mainly sinking motion, and therefore the air is very dry compared to the, of course, wet surface we are over the ocean. So that difference will give us evaporation, but then also we have strong trade winds. So the wind speed may be very high. And therefore in these regions we get a lot of evaporation. Now, as you already know, those regions where we have a lot of evaporation do not coincide directly with regions where we have most of the rainfall, which is shown in the figure here. Again, annual mean, long-term average picture here. That can be analyzed in much more details for whatever case study you want to do, but this is just the overall picture. And it tells us that those regions do not coincide at all. So that means there's a very important hydrological cycle going on. So water vapor that is gained in these regions is transported around and is condensating somewhere else and then flushed out as precipitation. Okay, so this is our basic relationship. We have in a stationary state, which for monthly mean values already, if you look at monthly seasonal mean values, is a good assumption. The storage can be assumed to be small. The storage may be important on a daily basis. Or of course, if you go sub-daily, then yes, even if the moisture goes up, the moisture, even if it's condensated, may not fall out immediately. There may be a delay of hours or so. But if you're already I would say in a weekly, if you do a weekly average or a monthly average, the stationary state condition is very well fulfilled. So there can be no storage in that case. So the precipitation has to be equal to evaporation plus this moisture flux convergence. This equation also has another implication, of course, intuitively. And you know this, of course, you know this, that if we integrate this term over the whole globe now, so we integrate this, that goes completely away because it's a convergence of, and we have periodic boundary conditions for the whole globe. So for the whole globe, we have that all our precipitation integrated, not only in the vertical now, but also in the horizontal direction, has to be equal to the evaporation. This is a good test. You can test this for reanalysis data and for any data set. That has to be the case. If that's not the case, for again, storage can be assumed to be very small for monthly data or even weekly data. So if you find a strong discrepancy between precipitation, globally averaged precipitation, and globally averaged evaporation, then there is a problem with moisture conservation in your model. Something is wrong. So whatever precipitation you find must have evaporated somewhere. That's the basic conservation of water vapor, of water in general. Now we want to look at an application of this to the Sahel drought phenomenon. So let's have a look at this a little bit small figure here. This is a satellite picture in a certain projection of the Earth, and it highlights regions that are darker and highlights regions that are bright. And of course, what stands out are here desert regions, and in particular the Sahara desert region as a very bright region. The reason is, of course, that there's very little vegetation there, and sand has a higher albedo than the forest that we have in these tropical regions. So now we want to concentrate on a very interesting region. As you know, and you can imagine, it's very tough to live in the desert, but it's also tough to live in the rainforest. But in this transition region, the conditions should be relatively pleasant. So this, what is called Sahel region, is this transition region between the tropical rainforest and the Sahara desert, where we have, on average, quite pleasant conditions because it rains, but it doesn't rain too much. But this region has some other problems. Let's have a look. So if we look at the rainfall now, the rainfall distribution, this is now for summer because this investigation will focus on the summer season. So the summer season climatological long-term rainfall distribution there. This is in millimeter per day. Green colors indicate large rainfall, and then yellow and gray go to 0. Then you will see again, as we were thinking already, this region here that is about between 10 and 20 degrees is this transition region between the large rainfall amounts in the inner tropics and the very dry desert region. And this is also confirmed by a quantity that you can also measure from a satellite, which is the leaf area index, which is defined as the quantity of leaves per ground area. And so this quantity, because of this definition, can go from let's say 0, of course, if there are no leaves, to 6 or 7 or something like this in this case. So the trees, the leaves and the trees overlap, and then they can have much more area of leaves if you put them one next to each other than the ground surface actually per square meter. So very dense forests can have a lot of leaf area if you were distributing them separately. And again, you can see that is consistent with the Sahel, where we have this transition. So this leaf area is sometimes used as a quantity that we can use instead of vegetation cover, for example. Okay. if we look at the rainfall standard deviation, and this is now for low frequency rainfall variability. So we have used a filter because the focus of the study is on decadal variability. We see that, yeah, there is some increase of standard deviation actually as we go to the north. So the standard deviation is not as highest where the rainfall is highest, but it's a little bit to the north. And this effect can be even more highlighted if you look at something that is referred to as coefficient of variation. So the coefficient of variation is defined as the standard deviation of rainfall divided by the mean rainfall. So that gives us something, is a useful quantity, because if you have a large mean rainfall, but interannually there's no variation of this, then you don't really care. Every year you expect the same amount of large rainfall. It's not important. Every year it rains like a lot amount and there's no variation. But if this quantity is large, that means that, you know, assume you have some kind of medium rainfall. So if this quantity becomes 1, that means that the typical variation of that quantity can be as large as the mean rainfall. That could mean that in some years, even if it typically on average there is rainfall, but that can mean in some years you have, instead of 1 millimeter per day rainfall, you have 0 or the double. So then that can have a lot of impact on your agriculture in that case. So this coefficient of variation is an important indicator of such potential problematic. And as you can see, what we refer to as the Sahel has a large coefficient of variation compared to other regions. It's still not huge. It's not 1 as quantity that I mentioned, but it is much larger compared to the other regions. So the Sahel region is a kind of a special region. And now, yes, now we want to look at a time series of rainfall. So instead of looking at the mean rainfall, let's say we define a box. And the box that I draw is not exact, but the exact definition is in these notes. You draw a box and you define the mean rainfall in this box. So you average the rainfall in this box, which is not very precise, but the precise definition is somewhere. Yes, so the box that we were concentrating on is between 15 west and 37.5 east and 12.5 north to 17.5 north. So just a 5-degree region that is indicating the Sahel region. So it's much, much narrower than the box that I indicated here. It's a very narrow box that highlights the Sahel region where we have the strongest coefficient of variation. And we look at the rainfall in that region, which is so important because many people live there because of these, in principle, favorable conditions. And so we look at the rainfall variation over the years in this region, and the average over this whole box. And if you do this always for the boreal summer monsoon season, because otherwise you also look at dry seasons and it may be more difficult to do a reasonable investigation. So if you plot just values for each year's summer season, you can see this distribution here. This goes from 1900 to just after 2000, because this investigation was done then. But what you can see here is something that has motivated many researchers to try to investigate this very interesting but also very problematic curve, because there were very wet conditions, for example, in the 1950s and 1960s in that region. So above normal rainfall. So this is here in terms of anomalies. So we have subtracted the mean. Therefore, we just see anomalies. So the mean rainfall in that region would be probably something like 2 millimeters per day. So we have a period with above normal rainfall, and then followed by, in the 70s, 80s, and 90s, a period with below rainfall. And the more tragic thing is actually that these are multi-year events. So whenever you start to look at climate, if that's your interest, to look at climate time series, this is very unusual, because usually we would expect have interannual fluctuations, more something that looks random fluctuations between one year and the other. But to get so systematic long year drought events is very unusual in climate. It's not easy to find. And it's very problematic, of course, because that means you can have decades of below normal rainfall. And then other decades where you have probably flooding in that region. So that is very problematic. And so researchers have posed the question, so what is going on? Why is this happening? There must be some systematic explanation for this. It cannot be just random, what is going on here. So what could one do, for example? Do you have any idea if we have, and the red curve that you see here is then a low pass filtered curve. So you remove the higher frequencies. You do, for example, a running mean of 10 years or 9 years. And then what you get is this red curve. And it highlights clearly these decadal changes. Now, what could one do in order to investigate this? So one thing what one could do is, for example, to take this time series and correlate this. A good candidate would be sea surface temperatures. Now we know El Niño is influencing global climate. So maybe that is some related to sea surface temperatures. And in fact, people have done that. So yeah, they have taken this curve, correlated that with global sea surface temperatures. And indeed, the El Niño phenomenon is something that comes up from that analysis. But then there are other ocean basins like the Indian Ocean and also the Atlantic that seem to play a role. But that's not the main issue here. So there is a clear indication that this Sahel drought phenomenon, or these variations in the Sahel region, that is forced by global sea surface temperature patterns. But those, in particularly, if you think of ENSO, that pattern is interannually varying and not so strong on decadal timescales. The decadal component of ENSO, there is some variation also, but it's much weaker. So this is still posing some kind of a puzzle. And then what you can do is you can say, okay, now I want to look into this more details. I take this period, this wet period and the dry period, and just look what is happening if I divide these two periods. I take an average over the dry period minus over the wet period. And then I do a spatial plot of rainfall. So that is done in this figure here. You look at the dry period, 80s and 90s, minus the wet period. And that gives us some indication of if this is just very localized or if it's a more very large scale pattern. And it is very large scale, as you can see. The whole Sahel region is very dry. These anomalies become very dry in this region. And then there's some dipole if you look to the south. So people wanted to investigate this. And Yes, so this is essentially what I said. So there have been so many mechanisms has been proposed. So the one mechanism that is probably has the most consensus is that the Sahel drought must be related to sea surface temperatures. But there's also a strong belief that land surface feedbacks must play an important role in the Sahel region. Now, there have been some more studies that indicate probably also human-induced land use changes and aerosol forcing may have played an important role. But the one role that we want to concentrate here in this lecture is the role of the land surface interaction with the atmosphere. In order to do this, we have to, if we have a simple atmospheric general circulation model, that typically has something like the typical setting is where you have a interactive soil moisture. So soil moisture is calculated. You assume that there is over, if we are not over the ocean, where we prescribe simply sea surface temperatures, and of course assume that there's moisture is always available, but over land, for the evaporation, to calculate the evaporation, we need to have some kind of model for soil moisture. And that model is typically present in climate models and in weather forecasting models. So there is some, it rains and that accumulates in your surface moisture, and then that can evaporate and so on. But it turns out that maybe we need to go a step further, because also the vegetation can be interactive. So but vegetation is usually in most standard models, particularly weather forecasting, but also climate models, is often just a prescribed quantity, prescribed climatology. It doesn't interact with the rainfall, for example, and sun. It's just prescribed. But in order to understand these feedbacks, one should have an interactive vegetation model. And so one equation that has been used, a very simple model of this type, is shown here, where it says a simple evolution equation for the vegetation cover. Vegetation cover can be between 0, desert, and 1, which is completely covered by vegetation. And then there can be several terms. So one term would here saying that there is some, if I have a lot of soil moisture available, then I expect that the vegetation should grow with some quantity. These are, in this equation, these are not derived from first principles, but these are estimated from field campaigns or from observations how vegetation is related to soil moisture and to, in this case, also availability of solar radiation, for example. Here's this other term here. So and L is again a function of the vegetation cover. So if vegetation cover is very large, then this becomes small, and then the vegetation just grows if there is water available. But then if the vegetation cover is not so large, then it's important how large this term is. And then there's some decay term. So if we don't produce any vegetation by having a rainfall and sunlight available, then at some point the vegetation will die if there's no moisture and no sunlight. So that is one of the equations that is used in such model. But another equation is very important for the atmospheric model, because in the atmospheric model, usually then also albedo is just a prescribed quantity. Albedo, which is very important because at the surface, albedo tells us how much of the solar radiation is absorbed and how much of the solar radiation is simply reflected. So albedo is a very crucial quantity for a model. And if we have a dynamic vegetation model, we can parameterize this. So albedo can be, the most desert regions we have has the maximum albedo, let's say 0.38. And then there's this term that tells us when we have vegetation cover, then the albedo is reduced to something that can be a minimum of, in this case, like over ocean. If we have dense forest, that is like an albedo similar to ocean, which is about 0.1. So this equation is the other equation that is used in such models. So that's what we want to do. We want to use a model that is now coupled, that has an atmosphere. The ocean is not, the ocean is just prescribed. We prescribe surface temperatures from the ocean. We could also couple it to an ocean model, but that's not done here. And there's a land surface parameterization, so land evaporation, and these processes are modeled. And then there's an additional component of a dynamic vegetation using this model, this one equation that we have just looked at, that interacts with the atmosphere through albedo and the evapotranspiration and so on. So we want to model now this Sahel drought phenomenon. Okay, so the outcome of that exercise was, so there were two experiments. One was an atmospheric general circulation experiment that was forced with observed sea surface temperature variation. So the only forcing are sea surface temperatures that depend on time. And in one case, we have the interactive vegetation, like in this case. In the other, we don't have interactive vegetation. So this not interactive vegetation setting tells us that we can model, even in that setting, we can model this Sahel drought. But it's much weaker than in the case where we have the interactive vegetation. That tells us that having interactive vegetation increases this persistence of drought and so on, or wet conditions. And the feedback mechanism is a very, very well-known feedback mechanism that is called Charney feedback mechanism. Charney has invented this feedback mechanism. So he said, okay, imagine there is from other forcings induced dry conditions, sea surface temperatures impose that there is a reduction of rainfall. What will be the impact on vegetation cover? As you can easily imagine, the vegetation will come under stress. So it will be, the vegetation will be reduced in that region when there is less rainfall, because there's less soil moisture to feed on for vegetation. That will have an immediate impact on the albedo, because if there's less vegetation, we have higher albedo. But that immediately influences the surface energy balance, because the surface will absorb less solar radiation. So the solar radiation shown here that is absorbed at the surface will be reduced. So the surface will have the tendency to cool off essentially. And you will create a high pressure over that surface with increased sinking motion. That increased sinking motion further reduces rainfall. So Charney has proposed this positive feedback mechanism between vegetation, albedo, surface absorbed radiation, and going back to precipitation. That is then responsible for this increase of the signal that can be induced by external forcings. So this is the mechanism that Charney has proposed. Precipitation is reduced, vegetation is reduced, albedo goes up. That leads to subsidence and further reduction of rainfall and so on. So there's a positive feedback loop going on. And then we were talking about this is an application also for this moisture flux vertically integrated moisture flux equation and the equation for the moisture balance equation. Yes, so we can investigate that also. How much in the Sahel this rainfall change is induced by moisture flux convergence or local evaporation changes. And quite surprisingly, maybe one would have guessed that it should be mostly induced by moisture flux convergence, because the Sahara is quite dry. But since we are in a region where we have already rainfall, there's quite a strong contribution already from local evaporation. So probably 30 to 40% of the rainfall response in that region is given by the local evaporation and the rest by the moisture flux convergence. And then, yes, we have investigated further the ingredients of this feedback. There is the high pressure that Charney has proposed should be there. Then as a response to the less absorbed radiation at the surface, a high pressure should develop, and that is the case. And so everything is consistent. So in this setting, in the model setting with the interactive vegetation, we ran not just one simulation, but many simulations. That was somehow able to mimic the observed structure of rainfall response, not on a year-to-year basis, but the overall structure of rainfall response was very similar. Whereas if we fix the vegetation, then indeed the rainfall had more like of a year-to-year variation and less persistent droughts. So there's a clear, this multi-year persistent droughts are clearly strongly affected by the effect that you have this interactive vegetation in the Sahel region. If that is not the case, then you may expect more year-to-year, just year-to-year fluctuations. Yes, so, but you know, this would be a typical result for climate models, that you cannot expect in such a setting to reproduce exactly the observations, because the atmosphere remains a very chaotic system. So we will discuss this in the last two lectures on Friday, that you know there is only so much predictability in the atmosphere. If we have a strong forcing from something, only then we can expect. So this result that we get here, that we can, from this ensemble simulation, many simulations, but there is some average signal here that indicates us that this Sahel drought is there at about the right timing. That is already some result. And then that is, however, very different if we look at the simulations where we have excluded this interactive vegetation feedback in the model. So that is supposed to be now, I think this is a very commonly accepted hypothesis, that the vegetation and land surface feedback are very important in the Sahel region, and then maybe reinforced by some other processes like aerosols and so on. Now we have to cover today one more topic, which is a little bit shorter, I think, which is the principal component or empirical orthogonal function analysis. It's a purely statistical tool in this case. Again, I cover this because no one else is doing it, and it's very useful to do it. Essentially, we are saying, so far we have tried with equations, sometimes treating the atmosphere very badly and taking a hammer and really destroying the equations governing the atmosphere to a minimum that we can use to extract some of the properties that we are interested in. So we have used the shallow water model, for example, to discuss equatorial wave theory and so on. And that was successful in some ways. But at some point, we may also come to conclusion, the real atmosphere is very, very complex. And we may not also always have easy ways to describe that analytically or doing some kind of analytical analysis. The same is actually true even if we model the atmosphere. That is true. Because the better our model is, the more realistic will this model be. So in the end, a very realistic model simulation may be as complex as looking at observed or reanalysis data sets. And you will have as much problems to understand what is actually going on in a simulation as compared to the real world, unless you do a very, very targeted, idealized experiment where you can extract some information. But just a climate simulation may be as difficult to understand as the real world, as looking at the real world. So there's not much gain there. So Lawrence, again, Edward Lawrence, the one who invented the atmospheric energetics, and who will be also relevant for the next lectures when we discuss predictability and we introduce the chaos theory. He also introduced this EOF. He introduced the principal component analysis, essentially in atmospheric science, and he called it empirical orthogonal function analysis. He essentially reinvented this method that was already there. So how can we motivate this? So the motivation I'm using here is simply look at some geopotential height anomaly maps. These kind of post-stamp maps are maps of geopotential, of winter mean geopotential height, 500 hectopascal geopotential height anomalies. Now, some people in Europe and United States, they are interested to look at these maps because knowing geostrophy, we can guess that the anomalous flow will be around these high pressure systems, in this case, in this direction, or if we look at this map, then in this direction. So this knowing also that the flow in the exotropics is very much barotropic, which means that it doesn't change much if we go from the surface higher up. Then knowing such flow patterns will give us an indication if this winter, for example, was a cold winter in Europe or a warm winter. For example, in this condition here, it was 56. In these flow conditions, these anomalous flow conditions, you would expect that there was a very cold winter because there would be an average anomalous flow from the northeast to the southwest in this winter. Let's see if there are some famous, if I find some famous cold winters, like negative NAO type. For example, this here would have anomalous northerly flow in the European region, and also this case here. This is a very strong pattern. It's strong easterly, so the westerly flow that usually brings warm air into Europe is strongly weakened. Anyway, the problem here is that in principle we know that these fields are governed by our thermohydrodynamic equations, right? This is what we know. But then we don't look at the field at a snapshot and then maybe the next day, maybe then we could see a wave propagation. We may be able to see our Rossby waves propagating. But we compare 1 year's field with the next year winter mean. So there's no way we can use the thermodynamic equations to try to understand what may have caused the transition from this anomaly pattern into this anomaly pattern. Because that's 1 year away. And the typical timescales of atmospheric, of Rossby waves, we know this already, is days, a few days for Rossby waves. So there's no way we can easily understand how this pattern, not even with a model, how this pattern translates into this. In fact, that is not the idea here. But Lawrence wanted to do something different. He looked at these patterns and found, oh, sometimes they look similar. So maybe there are some preferred patterns. So if I look at this here in 58, and if I look at this in 51, maybe there's some similarity. Or sometimes they can be almost exactly the opposite from each other. So this again has some similarity with this. Maybe I've by chance picked patterns that are have mostly one sign here. So there seems to be some recurrent pattern, right? But here maybe something opposite, exactly the opposite going on compared to this, for example. This would be a warm winter because we have this warm air, then advected, sorry, the warm air advected in this direction. So Lawrence found that maybe there are some recurrent patterns here. There are some preferred patterns. And he wanted to say, okay, I want to analyze this systematically. Because if that's the case, then maybe, the atmosphere has so many degrees of freedom, as many as we have grid points essentially in our data set. So many, hundreds of thousands, maybe millions, depends on the discretization that we use in time and in space. So many degrees of freedoms in our Navier-Stokes equations. But maybe, looking at this, it looks like that's maybe not the case. There may be some low frequency, preferred low frequency patterns here that are recurring. Sometimes they switch, but maybe they repeat each other. So we want to do some, if you want to, maybe nowadays you would call it pattern recognition here. We want to apply a pattern recognition to these fields. What can be understood from this? Can we gain something? That was exactly Lawrence's aim, to investigate if there can be some structure here, if he can find some structure. And so that is this empirical orthogonal function that he proposed. He says, I want to express these anomaly fields. And this is the trick, if you want. That is already the trick, the solution. In order to simplify this, I think there are similar patterns. They are just patterns that depend on X and Y that are very similar. Maybe in this case, they would be identical if I just take one of these patterns. And there can be a time series. Of course, if they switch from -1 to plus sign, then there can be a time series attached to it. So he called these patterns that he thinks he sees in these time series of geopotential height anomalies or anything you can think of. He calls them EOF pattern. And then the time series attached to each of these patterns, he calls them principal components. And so by definition, the principal components should only be a function of time. And the EOF patterns here should be a function only of X and Y. So they would be the spatial maps that we have seen. Now he says, we can in principle express our whole data set in this new way, in this new coordinate system, if you want, if we add enough of these components. It turns out if you add as many components as we have number of grid points, then we can express exactly the whole field that we have looked at. So there is no information loss here in principle. This can be done. You can express these anomaly fields in space and time exactly by using simply this distinction between a time-dependent principal component and these many, many, many empirical orthogonal functions. But so far we don't have made any assumptions on these. Now the hope of Lawrence was, maybe if I'm very lucky, there is just one Maybe I can be lucky and there's just one. What happens if there's just one pattern? Then that would just one pattern. It's always the same pattern that I multiply with the time series, but the pattern is always the same. So it can switch sign, can become zero, can become large, but it's always the same pattern that I see there. That just becomes more powerful or less powerful or can switch sign. Then I have expressed the very complex looking data set in a very simple way. If it's just one pattern that switches from one year to the other sign, or that sometimes becomes larger and weaker. Or maybe not just one, but just a few patterns that are there that switch sign and that change in time. Then I'm very lucky. Then I have expressed my complex data set. And this data set can be as complex as you want. Now we have been looking so far at winter mean, but we could look at daily data and try to analyze what's happening in daily data or whatever. So this data set can be as highly dimensional as you want. If we are lucky and we can express it with a very low dimensional space, then we really found some structure in this data that is very useful. Also, if I want to exchange data with you and I find, oh, I can express my data with just a few of these components, then I just give you this principal component and the few EOF fields instead of the whole three-dimensional data set. Or the data set can be four-dimensional, but we assume here it's simpler. So if we deal with this, we are typically now discretizing again. Here we have already done some discretization, but now we discretize again in space and in time. And so we are dealing with, instead of with these fields, we are dealing with matrices and vectors. So let's say our data matrix can be written in this way, where time runs in one direction and space in the other. So we have assumed that we assume there's just one spatial direction, which is this, or if we have an X and Y component, we may construct a vector that is just much longer, that if we have M and N in space, then we create a K-dimensional vector that is N times M. So we can just arrange our matrix in a way where we put one of the components of that matrix behind the other and create a very long vector. That can be done. So for our simplicity, it's easier to deal just with two-dimensional matrices. So we can say that this is just a spatial dimension here, and this is the time dimension, and this is the spatial dimension. So this is our data matrix. If we deal with any grid point data, and also data will always be discretized in time, this is the real world. If you download a data set, that will be some matrix like this with many data points. Then there's a way, it turns out that this procedure that we are applying has always to be based on anomalies. Anomalies in this case, for simplicity in time. So we have to subtract a time mean. And here's just written a simple way to define a time mean. You divide 1 over the number of time steps, and then the one matrix applied to the data matrix. You can very easily verify that this removes the time mean from each component in our matrix by applying this to a 2x2 matrix. So then you kind of subtract always the time mean from each of the component. But we can also assume that our data already is provided as anomalies. So we don't have to deal with this. But if you don't have anomalies, you have to remove the time mean from all your data. And then you can assume now that our anomalous data can be expressed now again as the sum over from L equal 1. I put here already K because it turns out the dimension we can put here is the number of grid points really. And then we sum up a principal component vector that just contains time dependence and the EOF vector that just contains a spatial dimension. And in order to create a matrix, you have to multiply these two vectors in such a way that they give a matrix. So you have to use one vector and have to transpose the others. And if you multiply them in this way, you get in the end the matrix back. So it's not a scalar product between them, but a matrix product. So now Lawrence says, okay, I have to impose some conditions. Otherwise, I don't know how to go forward here. And one of the imposed conditions is a very useful condition. That means that, okay, in order to get an order here, it's for me very useful if one field is orthogonal to the other. So if I multiply one vector, one EOF scalar with another EOF vector, then if those vectors are not the same, then that spatial correlation, if you want, between these two vectors, so that scalar product, that should be 0. So one field should be uncorrelated with the other field spatially. Or that's the normalization. If they are the same, then this is 1. So I have to use some normalization. But if that's the case, we know already that then the dimension has to be carried, the dimension of the field that we have then has to be carried by the principal component. Because in the end, we want to express, let's in our case, geopotential height data, or we want to express sea surface temperature data. With this, actually, there's an interesting feature, because if we project our data, so if we multiply our data matrix with an EOF vector, then because of this orthogonal unit vector property, that gives us just a delta LM, and so that projection gives us the principal component. So whenever we have decided on a EOF vector, we don't have to do any calculation, any special calculation anymore to get our principal component time series. That is given. Then I just apply our anomalous data to that vector, project that on that vector, we say, and we get our principal component time series. So if one is known, the other is known in principle. There's not much complicated calculation. Now, however, what is the criterion? How do I want to define this EOF? And that is very clear. So we want to minimize the residual. We take the original data, but we want to express our data in this new space defined in this case, for example, by just one pattern. How much of the data can we express by just one pattern? And if that explains everything, if just one pattern, maybe changing with a PC multiplied, so changing from year to year, can explain maybe our whole data set, then this residual would be 0, and we are done. We have minimized this. 0 is a minimum in this. For practical reasons, that will not be the case, but this is our aim. If we can find one pattern that explains everything, we have solved the problem. So we want to minimize this residual. And and the meaning of this residual squared is that we have the variance. Essentially, we calculate the variance of these values. The variance of y in this case, so the variance of this difference. Now, it turns out, if you look in the textbooks that this problem can be transformed into another problem. So you can show that this is also equal to minimizing that square minus that square applied to E1. And since this is we are varying with respect to the EOF vector, so that is independent of this. So that means that minimizing E1 also means maximizing this minus quantity here with respect to E1. Now this Z times E has a special meaning. That's again the projection. That's the projection of our data on that EOF. So that gives us some interpretation of this quantity. So we try, if we have data, let's say just now in this two-dimensional space, we have a data cloud. And the EOF would be to find in this two-dimensional space two axes essentially. So what we're trying to do is we project all these data points on, for example, this line here, and try to maximize. So EOF tries to maximize then the variance in that direction. This is different from linear regression because we try to maximize this. So it turns out that this is a very well-known problem in physics and has been solved for many physical problems. And the mathematical solution is that again we are solving an eigenvector problem. So a matrix, which is the variance-covariance matrix, which is a k times k matrix. So if you imagine we have many grid points, maybe we have 100,000 grid points. Now this variance-covariance matrix would be 100,000 times 100,000 matrix. So a huge matrix, which contains the variances and covariances of our data. So all the information of our data, how they interconnect spatially. That applied to the EOF is equal to an eigenvalue times the EOF. So it's an eigenvector problem, which can be solved. So this eigenvector problem, we know we can solve this. We have solved eigenvector problems already many times. How to do it? We have to set the determinant of S minus lambda essentially to 0, and then we can make the calculation. That gives us non-trivial solutions of this eigenvalue problem. Assume we have solved that we have found the solution for the first eigenvector. Then either we are done if we have explained the full data, or in most cases we are not done. We have to solve it for a second EOF, and so on. So we go iteratively on like this until we have explained the whole data set. And it turns out, since this matrix S is a k times k matrix that has k eigenvectors, so we can find k of these eigenvectors. So our sum of our EOFs has to be as large as is the spatial dimension of our data set. So if we have 100 times 100 grid points, that is 10,000 times, then we can find 10,000 of these EOFs. And then if we add them all up, we can express the whole data set completely. But we don't, this is not our aim really. Then, okay, we haven't gained much. We hope for something else. Because we know that the polynomial that we get from this setting the determinant of this, so we get S minus the identity matrix lambda, and the determinant of this is equal to 0. Now we know that degree of the polynomial that we find here depends on the dimension of the matrix S. If that's a 2 times 2 matrix, we can find 2 solutions. If that's a K times K matrix, we can find K. We get a K power. The maximum power is K in this determinant here. And so we get K solutions. But our hope is something else. So some more properties here. It turns out, and you can show, if you want to, that also the principal component time series, another very useful property, the principal component time series, if I take one with the other, different ones, then their projection, their scalar product is 0. That means they are uncorrelated. If I calculate the correlation between the first principal component belonging to the first EOF and the second principal component belonging to the second EOF, then their time correlation in this case, not spatial, but time, is 0. But what we hope really is that we can express most of our data already with a sum that is much smaller than the number of our grid points. So maybe we are lucky and we can express 90%, let's say, of our data already with 10 of these. So instead of 10,000, which is the number of grid points, maybe we can have 10 or just a few. Then we are very lucky. A few further properties are that if you add up all these lambdas, that just is the total variance of our data set. But that also means that if we have, for example, found the first lambda, the first eigenvalue, and divide that by the sum of all eigenvalues that we can find, then that is the explained variance by that eigenvalue. And we know the first eigenvalue we found is the largest one. So the first EOF would explain most of the variance of our data set. And then the second one, and so on. There's another important property that is very relevant and that is actually used also in the exercise data set that I've provided you already on the Slack channel, a tar file with a Fortran code that can be used to perform an EOF analysis. And that is, instead of solving the original problem, which led us to a K times K matrix, you can solve the transpose problem, which leads us to an N times N matrix. So if it turns out that our time dimension is much smaller than our spatial dimension, it's convenient to solve the transpose problem, which has exactly the same solution. And that is typically done in climate variables because typically we have more data. Our spatial resolution is such that we have more data points in the spatial direction than we have in the time direction. But that may vary from problem to problem. Okay, so the geometric interpretation of EOFs we have already discussed. So what is the interpretation of EOFs then? So our hope is really that if there is a strong low-dimensional physical mechanism, such like ENSO, which we have discussed already in the Pacific. So ENSO is we have found a very large-scale phenomenon that influences the whole Pacific. If such a mechanism exists, we hope that our statistical analysis that we apply to a data set, so we apply now, let's say, an EOF analysis or principal component analysis to the sea surface temperatures in the tropical Pacific, then our strong hope is that the first EOF, and related to the first principal component time series, that will be ENSO. In fact, this exactly what I just said is the case, and this is often used as defining ENSO. So you say ENSO is not if you provide a time series, is not an index defined over some specific region in the Pacific, but you say ENSO is this first EOF pattern that I have found. And the corresponding time series is the principal component time series that statistically belongs to this pattern, to this most powerful pattern. Often, EOF analysis is used to define indices, to define patterns and indices, instead of just saying, oh, I take the difference between here and there because I like it. You say, oh, I don't understand much about the data, but what pattern explains most of the variance in our data? Is there any pattern that stands out? And then I perform an EOF analysis. I find this pattern. Oh, this is the most powerful pattern. And the time series is this. And this is now our index for that pattern that I call whatever you want. So for the Pacific, it turns out for Pacific sea surface temperatures that ENSO is the first EOF. Turns out to be the first EOF. Now there's a problem. So the other way around is often not the case. So you have a data set where you really don't know, you don't have any expectation from physics. You don't know that there's any low frequency pattern that is outstanding that should govern the data set that you're looking at. But you perform an EOF analysis. You say, oh, I'm still interested to see if there's any preferred pattern, if there's any very powerful pattern compared to other patterns that governs this data set. And then you find this, EOF gives you also always a pattern. But then it may not be easy for you to find a physical explanation for that pattern. This can be a research exercise. To find a physical explanation for an EOF pattern could be a typical research question for a PhD or something like this, definitely. More problematic are higher EOFs because, as we know, one is defined to be orthogonal to the other. So if we look at higher order pattern, they typically have more structure by definition because they have to have. If the first pattern is just like ENSO, very large scale, then the next pattern has to be just adjusted that the spatial correlation is 0. So there have to be more nodes and so on. So if you look at very high order EOFs, they typically are very scattered around, very anomalies that are scattered around. And the explanation, the physical explanation may be very difficult. I just want to mention that there are many other methods that are also relevant. So this EOF analysis is the most basic analysis that you can use to dig into big data sets. To kind of, if you want to do data mining. Now people are talking about big data and data mining and so on. The EOF analysis is the most basic tool to do some data mining. But there may be other tools that are then often based on EOF analysis. So you often use the EOF analysis anyway to do some filtering of your data. But there may be some, for example, a question, if I have a geopotential height field or surface pressure field, how is this related to sea surface temperatures? And that question I cannot answer necessarily with EOF analysis. If I'm lucky, and in the exercise that you will do, you will be lucky that applying the EOF to do different fields, applying EOF analysis to different fields, gives us the first principal component for both analysis, and they are very highly correlated. Then the conclusion is that I have found the same physical mechanism. And this will be done in the exercise that you do. So if I'm applying an EOF to the surface pressure in the North Atlantic and in the surface temperature in the North Atlantic, and the patterns, of course, they have different dimensions. But if the PC, if the principal component time series are very highly correlated, I can simply assume that these fields are physically related. So one is forcing the other. essentially, or they're coupled, depends. So a systematic way to analyze, if we are not that lucky that that is the case, a systematic way to analyze this is what we call canonical correlation analysis, that can systematically find two patterns of different physical fields, find the maximum, the patterns that show then in the time series of their principal components, the maximum correlation. But we will not do this here. Just as an example, going back to our EOF of the northern hemispherical flow. So this is the outcome. The first EOFs, if you apply this principal component analysis now to this, to the many fields that we have seen. This is the first pattern that appears. And remember, the sign of the pattern is completely arbitrary. I could multiply this by -1 and get exactly the opposite. The pattern is a linear analysis. So the pattern, if I reverse the pattern, I just have to multiply the time series by -1. So the pattern has no meaning. There's no meaning in having positive sign here or negative sign of all these anomalies. That is exactly the same physical meaning. But for this first EOF, actually, there's a physical, that is a very well-known pattern. This is called Arctic oscillation. You may have heard about this in current weather. Or maybe in the North Atlantic part, you may refer this as to the North Atlantic oscillation. So this is a very important variability pattern in the North Atlantic or in the whole Northern Hemisphere altogether to govern climate anomalies on interannual timescale in the northern extratropical regions. And this is actually also here, EOF analysis is used to define this pattern. It's not that we say, oh, we know that there is Arctic oscillation, we define it like this. No, you use EOF analysis to define this pattern. So the Arctic oscillation is by definition the first EOF of the northern hemispheric extratropical geopotential height at 500 hectopascal, or at the, depends, or of the surface pressure, sea level pressure, and so on. But the EOF analysis is not just something, but is very often used to define climate pattern and climate indices. And that is for this Arctic or North Atlantic oscillation the case. And also the second pattern here is a well-known pattern. This is the second EOF, explains, I don't have written here how much variance they explain, but maybe the first, let's say, is explaining around something more than 30%, and the second then maybe more than 20% of the total variance. So these two together, they may explain already 50% of the variations of the whole data set that we are looking at. And then we have to add more EOFs to get to, let's say, 90%. But sometimes 10 are already enough to explain, for most of the climate data sets are so low dimensional that maybe 10 EOFs are enough to explain more than 90%. So this also, the second pattern is a well-known pattern, and is called cold ocean warm land pattern. But there's the whole story behind this. So I encourage you to perform the exercise. So you have desktop PCs, right? So you can run Fortran code on that by definition, because you have done the numerical methods course. So I've put on Slack a tar file that contains a program. And I'm asking you to use this program. It's already predefined, essentially. What I cannot guarantee is I hope it runs on your current PCs. If not, you may have to change the compiling options to something that you have used Fortran compilers already, so you know what are the compiling options in your settings. So let's see if this works. So I'm asking you to do this exercise. It should be straightforward, just changing one data set to the other, essentially performing two EOF analyses, one on the surface temperature and one on the geopotential height in the tropical Pacific, and then perform an interpretation of the patterns and time series that you see, to do some research into this, let's say. Okay. So this is it for today. And on Friday, we discuss the last chapter, which is the predictability of the atmosphere, which comes back to some of the issues we have already touched on. The atmosphere is not highly predictable. And if we want to make seasonal predictions or climate change predictions, of course, this turns out to be a big problem. So we have to understand what is the predictability of the system that we are looking at. Okay. Thanks a lot. See you on Friday.
Thank you.
Bye.
Thank you.